Thank you. And hello, PyCon. How's it going? Interesting so far? Good. So, my name is Peter Mascolo, and I work for Optum Ireland. I will tell you about us in a little while. And my talk today, I just want to make sure that no one is in the wrong room right now, will touch these points. I will quickly introduce myself, because I'm not rude. I mean, I'm a bit unpleasant, but not rude. I will define and tell you how to represent Markov chains, and I'll show you a bit of maths, a bit of code, and a live demo, very small demo, of how this can be used and how we're using this. So first things first, this is me. I'm a physicist. You weren't meant to see that. I've been working with code for a while, mostly with Python, but I have many other interests when it comes to code. I am a ham radio operator. You will see my call sign, IZ4BB, in all my handles. My GitHub, my Skype, my Twitter, everything, basically. And I have a few other hobbies. But now I want to talk to you for a couple of minutes about who we are as a company. Has any of you ever heard of Optum? Raise your hand if you have. There's never anybody who has heard of us. Let's try this again. We're part of a bigger group that is called United Health Group. Has anybody of you ever heard of that? Nobody. Great. So, this is who we are. We're actually a pretty big company. We're ranked 6th on the Fortune 500 list. And we work mostly around healthcare, trying to improve it for everybody. So we work a lot with technology and with services revolving around healthcare. And as far as I can remember, in the last corporate email I saw, we've just hit the 285,000th employee. So it's a big company. And if you're interested, we are hiring in a crazy way. So just look for us, optum.com. Plenty of job offers in there. All right, let's move on. What are Markov chains? Sorry. First, I want to define why we're doing this. So this sparked from a real project we were working on a few months ago. I can't tell you a lot about the internals of the system, so I will have to keep everything as anonymized as possible. I apologize for that. It would be very vague. So basically, we have a system. Our users, our members, use the system, and they go through a sequence of steps. Each of these steps has an outcome. The outcome can be good, can be an error, or it can make everything die. Doesn't really happen, but technically it could. And some of these sequences of steps lead to bad outcomes, like for example, customer churning. And some of these are actually good outcomes. We want to get there because it saves us time and money. So our main problem was to find out how to detect which of these are good, which of these are bad, how to understand what drives the bad ones, and how we can mitigate them. To do that, we decided to do a Markov study. So basically, we have a sequence of steps, and we want to know how they depend on each other in the sequence. So what is a Markov chain? Well, in layman's term, Markov chain is just a collection of random variables x with t, having the property that, given the present, the future is conditionally independent of the past. Easy, right? Maybe not. Okay. Maybe we can do with an example. So let's suppose we have a sequence of numbers. I'm using numbers to make it easy. 1, 2, 1, 2, 1, 2, 3, 1, 2. So given this sequence, we can say that if we are in the state number 1, there's a 100% probability we're going to be in state number 2 at the next time. If we're in state 2, there's 63% probability of evolving to state 1, and 33% to go to state 3, and so on. And that's driven entirely by the sequence. With me so far? Oh yeah, I forgot to mention that this talk was initially supposed to be 45 minutes, but I've just been told that it has been moved to a 60 minutes time slot. So if you have any questions, even during the talk, just raise your hand, and I'll try to answer it, okay? Okay, moving on. Those states, this is based on the same sequence that you've seen a minute ago, can be represented in many different ways. The two most common ones are matrix representation, which is very useful because it allows us to do calculation on it, or graph representation, which is very useful because it's really clear. I mean, it's really easy to see what's happening there. But what can we do with this? So we need a bit of maths, and sorry, bear with me, to understand what's in there and how we can use them. So first of all, this is the formal definition of those graphs, that graph I showed you earlier. Given a state I and a state j, if we're in state I, we have a certain probability of going to state j, we'll define it as Pij, and we have a probability of remaining in the same state. And that will be called PII. So basically, if you have a look at the indices at the bottom of the state or the probability, you will understand where are we moving from and where are we going to. Given those states, you can collect them in what is called a transition matrix. This defines all possible transitions within our systems, and this is based solely on the data that we have, so on all the sequence that we have. And we can calculate what the next state will be if we know where we are at right now. And that's basically just a matrix multiplication. We take our current state, S of I, we transpose it, and we multiply it by the transition matrix. And that will give us the next state. Well, it will give us a vector of the next state. It's a mathematical representation of probabilities. So if we go back for a moment here, suppose that we are in state number 2, which is the second row on our matrix. If we're in state number 2, that state is represented as a vector of 0, 1, 0. Is that clear why I see people nodding? Okay, I'll take that as a yes. If we multiply that column vector 0, 1, 0 by this transition matrix, we'll actually just get the second row. So that means that we have a 66% probability of being in state 1 and 33% of being in state 3. That's all there is to it. Okay, and these are probabilities, so these vectors must sum to 1. Okay, these are very simple. These are first order Markov chains. So basically, we have an element in the sequence, and we know that we know where we'll be in the next time step. But what if we are interested in more of the past? So what if, for example, we're in state I, and we want to know where we'll be next, given that we were in state J before? We can define something for that. These are called high order Markov chains. And basically, instead of defining the same transition matrix for single states, we do that for pairs, or triplets, or so on. Any number of elements. The problem with that is that the higher the order, the bigger transition matrix will be. Depending on the number of states, if we go from order 1 to order 2, we basically go from a matrix of about n by n rows and columns to a matrix of the order of n squared by n squared. That's a huge jump. And if we go for triplets, then we go in the order of n cubed by n cubed. So it grows really fast, and it becomes really computationally problematic. Now I will show you some code. I just have to give you a fair warning first. These are slides. I had to omit a lot from the code. So don't try to run it. It probably won't work, and if it does work, you will get weird results. I just want to show you what the implementation of such a system would look like. So let's create a Markov chain class. And let's start very simple. Reasonable? That was easy. Okay. Moving on. We have to define an initialization. So basically, when we instantiate our class, we need to define our transition matrix, and we need to set the order and the possible states. So we need to know in advance how many possible states we have. So let's do that. Let's assume that by default the order would be 1. Let's keep things simple. Having done that, we need to know what are the possible states, which is, I'm going to use a range of numbers. So if we have, let's say, 10 states, I'm going to use the numbers from 0 to 9 to identify them. Fair enough? Okay. But if we have an order higher than 1, those states will not just be the possible states, but it will be all the possible pairs of states. And at that point, we'll need to know that state 0 associates to state A, comma B, for example. And state 5 is C, comma D. With me? All right? If I see you nodding, I just keep going. Okay? Let's do that. So we just enumerate all states that we have using an itertools product. So this is what is giving us all possible combinations, pairs, triplets, or depending on the order. And we associate them with a number. In this case, we just use the range. We're using enumerate. See some blank stares, but okay. And given this, we have to now initialize our transition matrix. And I'm going to use a sparse representation for that. Has any of you ever worked with sparse matrices? Your hands if you have. Okay. The others, do you know what a sparse matrix is? Let's make it easy. Who doesn't know what a sparse matrix is? Okay. Not too bad. So basically, a sparse matrix is a container, and we know that it's all zeros except for some defined positions. So we don't need to store all the items in memory. We just need to know where the non-zero items are. And in our case, it's necessary because the number of elements in these matrices will be huge. So let's do that. We define our transition matrix. I'm using a dictionary of T matrix because it's very fast to initialize. I won't be using it as is for operations because CSR matrices are more efficient for that. So we now have this transition matrix of dimensions possible states by possible states. And if we have quite a few states and high order, that matrix would be very, very big. Yes, please. Yeah, okay. The question is where sparse is important. I'm just repeating because of the microphone. Sparse is scipy.sparse. It's a module in scipy. Sure. So the question is if we know when a combination of two pairs or triplets or whatever is impossible, correct? There's no graph yet. Yeah. Yes, okay. In that representation, yes. Yes, the states will be the nodes. Yes. That's correct. So we have all possible transitions here, but those that are impossible will have a 0 stored there. Okay. So that was just initialization. This is relatively easy so far. Okay, we have our matrix. We need a way to update the weights of transitions when we see them happen. And we can do it relatively easily. So we get a state sequence in, and we have to detect all transitions in that sequence, and we do it by this. It depends on the order, so if we are at order 2, we basically see what pair of elements goes into what pair of elements, and we do that for the whole sequence. And based on all these transitions, we can update the count in the transition matrix. So if we see that transition happen, we go to that corresponding element in the transition matrix, and we add 1. With me so far? Still blank stares, people nodding. Okay. Right? Okay. But something is missing though. Well, we're missing an S, definitely. But something is still missing. Any idea? We update our transition matrix, the counts of transitions. Sorry? Normalization. Yes, they have to be probabilities. So all rows must be normalized to 1. So we just add that. We just take the matrix and we normalize it row by row. And then, yes? Yep. Yes, you move from pair to pair, triplets to triplet, and so on. It depends on the implementation. In my implementation, yes, because we're interested in just in pairs. But depending on your implementation, you can just add the next state. Yep. No, transition matrix has to be square. Yep. Well, it's square because it's always possible states by possible states, so it will always be square. So the question you asked, I don't have a laser pointer, I think. I don't? Okay. So it would be the third last line when I take the element at state index plus self-order. If I remove self-order, I would just add the next state instead of moving to the next sequence. So instead of doing AB to CD, I'll just go from AB to BC. Okay, so let's write a quick utility function. Update transition matrix only works on one sequence, but we want to, do that in batch. We don't want to do that. We don't want to call it for n sequence, so we just have a quick function that does that for us. Nothing fancy there, and at the end it normalizes everything. Okay, now we need to predict. So how do we do that? If you remember the equations you saw earlier, the state at the index at the time I plus 1 is given by Si transposed times t. But what if we want n steps? We don't want just one. We want to generalize this. So S at the time I plus n is just S at the time I plus n minus 1 transposed times t. Any objections to that? I'll take that as no. But that item, S I plus n minus 1, is literally just S with I plus n minus 2 transposed times t transposed times the position matrix. And so on. This is a bit unwieldy to implement, isn't it? But wait. If we do take this all the way down to S of I, then we're basically left with just S of I transposed times transition matrix to the power of n. Any objections? I'll give you another 2 seconds to object. Cool. This is something we can implement easily. And the implementation is just that. We take a state. We have to know how many steps we have to go into the future. We take the power of the transition matrix. We then p dot power. That's a matrix power, so the transition matrix has to be square for that. Well, it has to be square anyway because. And we multiply that by the sparse representation of the current state. And that's all there is to it. There you go. The implementation is there. We don't need anything else to start using it. I mean, in the actual code, there are a few other functions that do other things, but this is the core. You don't need anything more than this to start using it. So I'm going to show you a very, very quick demo. If everything works, it should. Hopefully. Is this big enough? Too big? Can you read it? Can you read it even at the front of the room? Okay. So, I have a small data set. I have a bigger one, but I'm going to use the small one because it's quicker to train, so it's still a presentation. So, let's load it. And here we have the data. So we have element and exit codes. These are basically the nodes that the users go through and the outcome of each node. So we need to take these two sequences, slam them together, and we can use those for our analysis. And also create a hash map because we're not sure. So this is a small data set. So we're not sure that we actually have 6,114 elements in there. There might be gaps. Let's make it a bit tidier. So we'll just create a hash map like this. We basically reset the count. I won't bore you with the code that does that. This is done. We have 288 unique nodes and 97 unique outcomes. And slammed together, there are 385 unique states. We can remove the old ones, and these are the new versions of our nodes and outcomes. And we can mix them together. We have to go from a sequence ABC and a sequence 1, 2, 3 to a 1B2, C3, and so on. And this function does that. Okay. To go down. Okay. Now, the actual code is in a sorry about that. The actual code of the implementation of the Markov object is in a repository on PyPy, and it's on my GitHub. I'll give you the link at the end of the presentation if you want to have a look. And you can just pip install it. The latest version is not up there yet, but it will be soon. So let's import it. Let's set our object. So this codes map is basically the reset map after I reset the range. And since it's zero-based, I need to know how many are there, so I need +1. Okay, this is our object. We can fit it. Done. It's only 61 sequences, so it's pretty fast. I have a bigger data set. It has about 4,000 records, and it takes a bit longer to train, about 30 seconds. It's not too long, but no. And these numbers big enough. Just to give you an idea of why we're using sparse matrices, we have a matrix that has, number is that? 21,970,650,725 items in total. That's a big matrix. And out of those elements, only 886 are non-zero. That's about 0.00004%. A very sparse matrix. And we don't want to have that in memory. And remember, this is only order 2 for a few hundred states, so it grows really quickly. Okay, at this point, we can build a very small dashboard to see what happens in our data set. I'll just set a few things. Are you familiar with the widgets in Jupyter? Raise your hand if you are. Okay, cool. I'm using that. All right, see this? Slightly smaller. Okay, so at this point I have all the possible states here. These are not all the possible states. These are only the states that have a non-zero transition in the transition matrix. I just filtered them because otherwise this drop-down would be way too big. And we can set the number of steps that we want, a threshold, because maybe we don't want probabilities that are too low. And I'll explain actual weight later. So basically, what this is telling us is that if we start from state 0, 361, in this case we have a 100% probability of going to state 200 and 323. I'm sorry, I can't be more explicit about what those states are. But no. What if we increase the number of steps? We might find situations in which there's a fork, and we can now see how many sequences go one way and how many go the other. And this is how we're using this tool. We're using this mostly for diagnostics. So basically, imagine that state 274 and 361 is an error. And we don't want to get there. We don't want to go there. Absolutely not. So we have a look at this graph and we go like, okay, if we don't want to go there, and 92% of sequences go there from this state, then we have to have a look at that state. That needs to be fixed. Here. All right. And there are a few. I remember there was a more interesting sequence here. Yes. So you can't know in advance how many forks there will be. So the bit of code that does this is a bit convoluted, but it needs to be, unfortunately, because in most cases you have a split of between two options, but in some cases you might have 3 or 4 or 5 or hundreds. And for each of those you have to calculate what the next step might be. And in some cases you can just remove the things that aren't particularly interesting. promise to tell you what actual weight does. Yes, this is clear. What actual weight does is basically going from this representation. This is telling us that from that node until the node 250, 361, 48% of sequences start from there and go there. In some cases, we're not interested in how many sequences follow a path from the beginning of the analysis. In some cases, we just want to know how many go from one node to the other, and we don't care about the past. And this is what actual weight does. So yeah, 48% go from 65 to 361 to 146 and 318, but from then, all of them go to those states. Clear enough? I saw a guy going like. And that's it. Do we have any questions? Yeah.
Yeah. So my question is, when you build a model like this, you need to have an idea of where you can fix your threshold of how much history you consider, because it may be that like only three sequences are relevant.
Yeah. That's true. But that should not be addressed within this library. That should be addressed before you start the actual analysis and visualization. So in our case, it was pretty simple because we already knew that we were interested in pairs because it was pretty much a given. It was a sequence of events and outcomes, and they were paired. So in our case, that was really easy to determine. Any other questions?
Thank you. Can you model with Markov chains also continuous problems, so where states are not discrete?
Continuous problems, do you mean for continuous time steps?
So when a variable changes in time, and this variable is not discrete like this one, but it's a continuous variable.
So you can compute values for continuous variables, but you can't use continuous time steps. I'm not sure I understand your question, though.
So my question is that you are modeling a sequence of events.
Yes.
Where the state is a continuous variable, a discrete variable.
Yes.
Right. Can you model via Markov chains also where the state is not a continuous variable, is not really a state of discrete step, but it's just a continuous variable?
Potentially, I would say that you can do that, but you'd need a way to model how the transitions work. And for continuous variable, I don't know if that's feasible. I think I read some papers about using some Markov model of one sort or another for regression, so that would be something like what you're saying. But I don't really know, actually. Never had to work with that sort of things.
Hi, thanks for your talk. I was just wondering, are you just making some assumptions about the stationarity of the Markov chain? Does it have to be stationary?
So for a curve problem, we knew for sure that the stationarity of this process was kind of guaranteed.
Okay.
As in, it wouldn't be guaranteed if the system changed or if the user base changed in a significant way. We don't see that happening from one day to another. In other cases, you'd have to make sure of that before you can just jump blindly into an implementation.
So it's an important thing to check before all this analysis.
Because if the Markov process is not stationary, then your transition matrix might be stale when you use it.
Exactly.
So yeah.
Okay, thank you.
Any other questions? No?
Okay,
We're done.
There are no other questions. Just one last quick thing. My boss and my colleagues will probably be watching this, so please give me a very big round of applause. Thank you, thank you. You're a wonderful audience.
We have another question.
Are you aware that your bosses will also hear this? You ask us cheering for you.
Yeah, of course.
Yeah.
It's perfectly in character. He knows me.
Thank you.